Well, there's only 5 of you. All right, then. We'll just wait.
Can you post the slides for today, please?
What's up, Jack?
Can you post the slides?
Well, that's an interesting story. It's not really a story. There's no slides for today. Today I'm going completely rogue, and I'm just going to do a virtual blackboard. So that the video will get posted, and that's the best I'll be able to do.
Cool.
We've been following Keenan's class pretty closely. Keenan is also, teaching the same. He taught it. I think he's taught it the last couple of years. He's teaching it again right now in parallel with us, and we're roughly keeping pace with him. And he's got a new course webpage for his course this semester. I've been following his course webpage from last semester, but I also occasionally look at what he's doing this semester. And he doesn't have any new slides. The new slides he has for the unit we're about to do is from a conference talk that he gave or a colleague of his gave. And it's really not appropriate for you guys, for any of us, for me, or I don't think it's an appropriate thing to go through. So I've been through a lot of that material. I'll talk about that more in a minute, but what we'll do is kind of a subset of the stuff that he did. And I'll refer back to some of the readings that he has posted and tell you what you all should be reading to kind of keep up with the class and what sort of assignments to do and whatnot. Let's give it, what do we got? 6, 7, 8. We got 8 now. So let's give it, I don't know, 2 more minutes. Maybe no Catherine. There's Catherine.
I just waved at my screen, even though my camera was off. How's everybody doing? Are you feeling this relaxed?
Oh,
They're beautiful.
maybe not.
Oh.
Never quite that relaxed. Cats are on a whole different level.
Agreed.
Gotta get that white beard.
I've had to move my work situation out to my garage, and my garage is not heated or air conditioned. And now that it's 90 degrees out, you may start seeing sweat drip down my face. Or if you see me bend down all of a sudden, it's because I'm taking off my pants, but none of you will know.
I can recommend highly a vest with ice packed into it.
Yeah, that's a good idea.
Yeah. Mm-hmm. Yeah. In a pinch, a wet towel around the back of your neck also very helpful. Yeah.
Very good idea. Yeah.
Mm-hmm.
And I'm afraid I've got big doors over here I can open, but that's the direction of the sun. So if I open those, it'll bring in air, but also all the sun. So.
On the other hand, you have a cool garage.
Yeah, it's got a cool window. It's a cool window.
That's really cool.
Brickwork.
You can hide from your family out there?
Yeah.
Nice.
Yeah. Yeah.
Yeah, but what about your shelves? Are they very sturdy?
They're on the other side of the garage. I can use those. We've split our garage in half. So this is the workspace side. That's the storage side.
You're living the garage dream right now.
I am totally, yeah. It's just garage all the time.
My next house is going to be like an RV and then a warehouse.
There we go. I like that.
That's like about the right ratio that I need. Or 4-car garage.
Yeah.
Tiny house.
And a bedroom. Yeah. Mm-hmm. Yeah. I like that. Are we going to get more? What do we got? 1, 2, 3, 4, 5, 6. We still have 8. I was hoping to wait till we got 10, but maybe we're not.
People are drifting onto KB time.
You're usually the early one.
That hasn't happened in months.
Oh, at least for this class.
You just got to be on time the first week, create that impression.
Yeah.
Yeah.
Haley's mobile.
Like it. I thought that
I
people,
needed snacks.
Oh, there we go. Oh, shit. I didn't have my coffee. Damn it. I'm going to start to really droop without my coffee. Oh, well.
okay, listen, I need to tell you the best idea I ever had.
Yeah. This is all being recorded.
Good, great. You're gonna go inside and you're gonna make yourself ice cubes out of coffee.
Ah,
And then when you make iced coffee, you put those in there, and then it doesn't water down your coffee while you drink it.
that is an excellent idea. I like that
You can
idea.
also make milk ice cubes too if you take milk in your coffee.
That is an excellent idea. I like that idea very much.
That happened in grad school, and I was like, PhD now, please.
That is a PhD worthy idea.
I solved it.
Yeah, watered down coffee, not good. Yeah. I guess we should just get started. Oh,
Yeah.
Jack left us though.
I want to hear about how the assignment is going, because I feel like I was getting lots of good Piazza content from like Maya and Max, like making some progress on learning about solving Poisson equations and stuff. Are people feeling like they're making headway? We've learned that I will give out any number of hints.
Yeah, me too.
As soon as even when you know the steps to follow, it's not easy to like work out any of those problems. So yeah, I don't think you're losing anything.
Well, oh, we got one more. Somebody showed up.
Luke.
All right, let's get started then. I think we've hit a critical mass. So we're going to jump into a new chapter on conformal geometry. And I was saying, well, most of you are already here, there's no slides for this chapter. What Keenan has on his webpage are slides from a conference presentation. And he himself also kind of punted on his own lecture for this unit because he just had his students watch a recorded YouTube video of that conference where those slides were presented. And it was like an hour and a half presentation, and he just told them to watch it in 2 sittings, and that would be 2 class days. But it was clearly at a computer science convention, and he was not talking to the same audience I think he would be talking to if he was talking to a bunch of undergraduates. So I don't feel like the things he was saying were appropriate for you guys. So we're going to have to just kind of go rogue. There's a lot of information out there that he has on his webpage. And I actually do want to, I'm going to share my screen. And wait, before I do this, yeah, let me share my screen. How do I do this? There we go. Share screen. Desktop one. There. We have links. Hopefully you're all seeing my desktop, right? Like a Google News page or something. Yeah, good. You've all, I hope, been to Keenan's webpage. It's linked from my webpage, and it's also linked on Piazza. If you go to here's my webpage for our course, and it says right down there. I showed you this the first day. It says class webpage, but you'll notice at the end it says spring 2019, which was last year. And if you go there, this is his archived version of last year's course. And I don't know how much he's changing things from year to year. I just wanted to point out he is teaching it this year, and he has an updated version of this webpage. So if you just Google Keenan Green, I've shown you this before. First of all, it's amazing to just go to his webpage and just look at the pictures here. And you'll start to see, like this picture in the top right, we're going to see today, a lot of the pictures from his papers he has imported into this course. And I think a lot of these papers are explained in this course you all are taking now. But if you scroll all the way down to the bottom, on the right column, right over there at the very bottom, it says DDG course, which is the course he's teaching right now. And it looks just like that other course webpage, but this is, if you look at the web address, it's spring 2020. So this is the updated version. It's pretty much the same. But if you scroll down, like here's his lecture on the Laplace-Beltrami operator. That's the last unit we did that y'all are still doing the homework on. And you can see this is the video. This is what he pre-recorded that he had his class watch for Laplace-Beltrami. And that was what we asked you to watch last Thursday. This is the link to it. If you go up, the next topic is conformal geometry. This is the reading for conformal geometry that he posted. It's different than the chapter 7, the reading on conformal geometry in the course notes. So there's actually 2 different readings. This is something I really wanted to clarify. There's this set of notes, it's 51 pages that he wrote up on conformal geometry that he has posted as the reading for his class. And there's chapter 7 of the course notes, the kind of book that he wrote for the course. They're quite different. They're very, very different. There's almost no overlap between the 2. And today I'm going to talk about what's in this reading. And on Tuesday of next week, I'll talk about what's in the book. And your assignment, both your written and your coding assignment, are more on the material in the book. So today it's just, I hope this is just going to be interesting stuff. It's stuff I do want you to read, but you can keep working on the Laplace stuff because it's not due till next week. And then next week we'll get into the material, the conformal geometry material that you will have your next assignment on. So I think the timing's going to work out okay in terms of like, I hate covering new material when you're still working on old material. So we are covering new material today, but it's not material you'll use on the next assignment. Since you're working on the previous assignment, I think that works out fine. Next week we'll cover new material that is going to be on the next assignment, and you can start working on it right away. Scrolling up more. So this is the reading on conformal geometry that he posted for his current class. These again are the slides and video for a conference presentation that he gave. You're absolutely welcome to watch those. If we go to the video there, you'll see it's 1 hour and 37 minutes, and it was given at this symposium on geometry processing in Paris, France. And there's Keenan just giving this video live. And if I go back, these are the slides that he was presenting at that conference. So you're welcome to watch those, but I found it relatively incomprehensible the first time I watched it. Maybe after we do everything, you can go back and watch it and you'll pick up more. The written assignment, I don't know how much of this will have you do. Catherine and I are going to talk about this. I don't think all of it's appropriate for you. But I think the coding assignment seems like it'd be good to go through. I haven't done it yet, and I'll admit there's 1, 2, 3, 4, 5 different routines you have to implement for this coding assignment. And at this point, I think I know how to do 2 or 3 of those. So I myself have to get up to speed. I haven't done any of them, and I'm not even sure how to do 2 of them. But by next week, when you all start working on it, hopefully I will have figured it all out and will have done it myself. So that's where we're at. Next week, we'll talk about, it's up here in this link, we'll talk about the spectral conformal parameterization algorithm for conformal mapping. That's a whole lot of words. You don't have to know what any of those words are right now because we're not doing it today. Okay? We're doing something different today. So next week, we're going to look at this reading right here. His assignment on this reading is to read 1.1, which is the overview, 1.2, which is preliminaries. Those are short. First, looks like the first 8 pages, but 3 of those are this table of contents. And then he told his class, pick either part 1, part 2, or part 3 to read. Just pick one of those to read. I'm not sure why he told his class that. And then if you want, as optional, you could also read part 4. I think I'm going to ask you guys to do something different, which is certainly read the overview and the preliminaries. And then also what I'm going to talk about today is really just part 3. I'll mention the stuff in the other parts briefly as we go, but I think of these 3 parts, part 3 is the most important and is the one I'll go through in detail today. Okay, so again, reading assignment, read 1.1, 1.2, overview and preliminaries, and part 3. And this is all on this document. I'm going to go backwards, that he's posted on his current course webpage. It might be on last year's too. I haven't looked. which is the reading assignment he posted for his class. And all of this we'll just post on Piazza as well. So you don't have to navigate to this webpage. I'm just telling you where it is if you want to find it. But we'll post links to everything, and we'll repost this document itself on Piazza. Good, is that clear what we're going to do here? All right. All right, while I've got my computer up, I want to show you a couple more things that I think are fun and kind of gets the point across of what it is that we're trying to do. So this is a sculpture I made. I've been 3D printing mathematical sculptures and things for my calculus classes for many years. This is one of the first things I did that I counted as sculpture rather than just a mathematical model of something. And I did this a long time ago. It's really one of the, about, I don't know, 7 years ago. And the goal was I had an actual seashell in front of me, and the goal was to parameterize an actual seashell as close as I could with a mathematical function. And then that's a whole other class that I teach on geometric modeling, how you take a physical object and write down a bunch of equations to replicate that object. The thing I want to draw your attention to here is not the object itself, but the coloring that's on this object. So the coloring comes from a photograph I found online of a seashell, an actual seashell, and I did a texture mapping to wrap that texture around the surface. I'm sorry, I'm going to step out for 1 second and yell at my son and tell him to stop playing piano. Give me 1 minute here.
I think it really adds something to the experience. Could be like one of those, like a silent movie where you have like the soundtrack going in the background.
Yeah. Last time I was teaching yesterday, he was playing guitar in the background, and I just let it go because it was a nicer soundtrack. Piano's a little loud.
Do I need to send a banjolele to your house?
No. Don't send any instruments to my house because he will start playing them. He plays drums, guitar, bass, harmonica, it's piano. So do not send any more instruments to my house.
Did you say a banjolele?
What's that?
This is like one of my favorite easy instruments. It's a ukulele, but it's strung. It's a banjo, but it's strung like a ukulele. So it's got the banjo head, yeah, and the strings, like it sounds like a banjo, but it's easy to play like a ukulele. They're wild.
Yeah. Well, he plays ukulele. You could probably pick that up too.
Oh, you're getting one.
All right, back to this. So texture mapping is a huge area in computer graphics. To make anything that looks remotely realistic, in practice, you're going to create some sort of three-dimensional model and then map a texture onto that model. So this is, video games work this way. If you have a person in a video game, very often, if you look closely, you can tell, especially in profile, you won't see a nose. Their face is just a sphere, and they've texture mapped an actual face onto that sphere. And when they look at you straight on, you can't tell, because you just looks like they have a nose there, because it's just a photograph. And sometimes there are slight tells, especially with sort of cheaper video games, where it's a really coarse three-dimensional model that they've mapped a detailed texture onto. A lot of video game processing is done that way. And it keeps the polygon count down, and you still get a really realistic looking object. And obviously in any of these animated movies and stuff, now they can have incredibly complicated models, but they still texture map on top of it. I do most of my three-dimensional modeling work with a program called Rhino 3D. It's one of the industry standard programs for architecture work, but most mathematicians I know who do any sort of modeling use this program as well. And a lot of artists I know. Here's Rhino. Rhino has some built-in texture mapping capabilities. And one of the things you could do is take a two-dimensional picture and import it. There's a picture of me, I import it. And then take an object, like a sphere that I made, and just say, hey, wrap this picture onto the sphere, okay? And you can see there's a whole lot of distortion, right? That doesn't look like me at all. I don't think it looks like, please tell me it doesn't look like me at all. Especially at the North and South poles. It looks like I have a necktie on, but if you look at the original picture, it's just my shirt. It's just a regular shirt I was wearing, but it's pinched so badly at the bottom that it's looking like a necktie. It's bizarre, right? So the inherent difficulty of texture mapping is being able to map one surface onto the other without distortion, right? And here's a really good example of texture mapping where nothing was done to minimize the amount of distortion, right? So that's what conformal geometry is invented, I think, well, these discrete conformal geometry. That's why there's so much interest in computer science. Catherine, you can correct me if I'm wrong, because I'm not the representative computer scientist here, but I think the whole point is that it's the interest in it is to create texture mappings that are where the distortion is as little as possible at every point on the surface. That's how I would say it. Is that a fair answer, Catherine?
No, that's all totally spot on. The other area where this is super duper important is when you have, could be something in 2D, or it could even be a 3D surface, and you're trying to deform that. So this is sometimes called posing, just like a person striking a pose. And that if you have a 3D model and you want to deform it in in certain ways, like you want to make sure that you're preserving the local sort of like areas, so that like the triangle on the arm doesn't like stretch out some huge amount, right? And I mean, that has super, super important ramifications, particularly when that geometry is going to be texture mapped, right? Because usually the texture is associated with particular sort of point on the surface, and you don't want it to be stretching too much, because then you get the distortion like you see here. And you also have that when you have people wanting to do something like 2D animation with drawings, right? That it would be really nice to be able to draw a character and then move them around with like a few control points, like, oh, I want to take this elbow and move it here, right? And being able to do that in a way that kind of preserves what makes that arm artistically look the way that it looks is really hard, and it gets into this notion of conformality.
Cool. All right, I'm going to try to flip over to my iPad screen here. And there's no slides for today, so I'm kind of going rogue. I didn't have time to make a set of slides. So I'm just going to flip between basically the document that I'd like you to read. That's the one I just showed you on Keenan's webpage. And I'll try to do a split screen and have like a virtual whiteboard going on the side. And I'll highlight certain parts of the document to certain takeaways, and then I'll talk about it more in like a virtual blackboard. So Jack asked about slides. So, I mean, your slides are essentially this document that that has been posted as a reading. And I'll post this video online as well if you want to go back to individual frames of it. I'm trying to share my iPad screen, and it always takes a couple of tries here. You are still not seeing anything. I've noticed there's just a long time lag. So I just have to wait, and then all of a sudden it seems to magically appear. Sometimes if I unplug it and replug it a couple times, it appears.
You can do it, Zoom.
It'll happen. It just takes a minute.
That's some really aggressive depth of field on your headshot.
Yeah. Oh, there we go. Yay. All right. Now I've got to just rearrange the windows that I'm looking at in front of me. I still see all of you. Okay, cool. All right. I'm in business here. All right, so let's go to this document as we were just looking at. So here's the table of contents, and then it just starts with this sort of general overview about what conformal geometry is. And let me see now, let's see if I can get fancy and notepad up. Oh, there's the Lyapunov exponents. Yes, it worked. Okay, so should be able to move this. Okay, cool. All right, so again, the idea is we've got some surface here. And it's got some contours and some, maybe a picture on it. And we're mapping it to another surface. So this is more like what Catherine's talking about, where we're going to look at a map from one surface to another and say, how do we introduce as little distortion as possible in that map? What we'll do next week is talk about maps just to the plane, which are more like that sphere flattening out to my picture. And then you can use a texture mapping on the thing on the plane and then do the inverse mapping to bring it back onto the surface. So that's called conformal flattening. So the algorithm, the computer algorithm you are going to implement next week is a conformal flattening algorithm, where what your challenge is going to be to take this three-dimensional object and flatten it out into a two-dimensional object with as little distortion as possible. And then the inverse map is what you would use to do texture mapping. Okay. Today we're going to talk a little more abstractly about just what does it mean in general if you have two surfaces, could be two flat regions of the plane or just two surfaces in 3 dimensions. And what does it mean to have as little distortion as possible when we have a mapping from one to the other? Right? So the most naive definition of distortion would be how much it changes lengths of things. So the measure of length between 2 points on a surface, that's called the metric. Okay. Metric is a measure of length. We kind of glossed over this early in the semester. You never really needed it for any of your assignments or for, and we didn't really need it for much of the lecture material. There were a couple of lectures I went in and manually removed all mention of metric in there because I didn't want to scare you or introduce anything technical that didn't need to be introduced. But metric in general, I mean, in a topology class, we would first define metric as just literally a distance measure between 2 points. It's a function which takes a pair of points in a topological space and returns a number which represents the distance between those points. That's what a metric is. In differential geometry, we talk about Riemannian metric. Riemannian metric is all that is a dot product. So it means if I have a particular point on the surface, we can look at all the vectors tangent to the surface at that point. And a Riemannian metric is just a way to do a dot product between those vectors. And so dot product satisfies certain axioms. So any function that satisfies the axiom of dot products is a Riemannian metric. Okay, now the point of that is if I have a way to take the dot product between vectors x and y, then that gives me a way, once I know how to take the dot product between 2 vectors, then I can take the dot product with a vector and itself, right? And the dot product of vector and itself is always what we define to be, this is a definition, the length of that vector squared. So inverting this, turning this around, if I want to know how long any vector is, I just take the dot product of that vector with itself and take the square root of that. Okay, so knowing what dot product is means I know how to measure lengths of vectors. And if I know how to measure lengths of vectors, then I can take any 2 points, draw a path between those, and do a line integral along that path to measure the length of the path, right? So again, the logic here, a Riemannian metric is just a dot product. Knowing the dot product allows me to define length. Knowing the length of a vector allows me to calculate the length of a path, and that allows me to define the distance between 2 points, which is the topological notion of metric. Okay, so inner product, dot product, leads me to a notion of distance between points. Does that make sense? Okay, so sometimes I'm saying all this because in a minute I'm going to use the letter G, and G is a function that takes 2 vectors, and I'm going to call that the Riemannian metric, and then I'm going to start to say things like, well, now how does the Riemannian metric affect distance? And you should understand what the link is between Riemannian metric, which is just dot product between vectors, and distance, okay? So in particular, I'll say this, if I look at this mapping from one surface to another, let's call that phi, okay? And I have some measure over here. So here's x, here's y. And at this point on this tangent space, I have some notion of the Riemannian metric. I know how to multiply x and y, right? And let's say at the corresponding point over here, right? So I'm taking, I should use some colors here. I got this point right over here, in red. I map that through phi, and I get this point over here. And if I also have a metric, I have a way to take the dot product between vectors here. If the metric commutes, so let's call this G tilde. So that's the dot product in the target space. If G tilde of phi of x comma y and actually technically that's d phi that maps the vectors. Sorry, I'm squeezing that in here. Now you know why it's better to do type slides. Let me rewrite that because it's horrible. If the metric in the target space with the image of x and the image of y carried over, if that's just equal to the metric in the original space with x and y carried over, right, then that tells me if the metrics are the same, the Riemannian metrics are the same, then all distances in the original space is the same as all distances in the target space. And so if I have a way to carry the Riemannian metric over directly, then all the distances are the same. That's called an isometric. Yeah, Catherine, I see you have your hand up.
Sorry, this might be super obvious, but why is it D? Because if x and y are vectors, wouldn't phi, or is phi taking the point x to the point x tilde?
Yep.
And then,
yep.
and then D, wait, but are x and y vectors or x and y points?
X and y vectors, yeah.
Oh, defined at point,
yeah,
whatever.
Yes, right, exactly.
Wait, so why isn't it phi of?
Yeah, let me draw a better picture here.
I just want to make sure my brain's working.
Question.
Oh, okay.
So, I don't know. Because like, is it a map from tangent? Is D a map from tangent spaces to tangent spaces, or is it like a map from surfaces to surfaces?
It's so funny because like we talk about this stuff in graphics all the time. Like, oh, like we would call this parameterization, surface parameterization, and it's like, oh yeah, well the map just takes the 3D thing to a 2D thing. But I never stopped to think, are you mapping points to points or are you mapping tangents to tangents?
Does that help? X and y are tangent vectors at the point P.
Ah, okay.
Phi maps a point in the original space to the point in the target space. So the differential of phi maps tangent vectors to tangent vectors. Okay.
Why don't you also add D on the other side?
On the right side?
Because it feels like it should be D something equal to D something, right?
So this is saying if I take two vectors at the point P, and then I map them to the target space, and then I compute the inner product between those in the target space. And the question is, do I get the same thing as if I were to just take the metric in the original space and apply that to the two tangent vectors in the original space?
Oh, so D phi is one thing.
D phi, yes, D phi is the map. Yeah, D phi is the map, the differential of phi. Phi is one way to say this, the fancy way to say this is phi is the R3 is an R3 valued 0 form. D phi is the R3 valued 1 form that takes vectors to vectors.
Okay, and what's G again?
G is the metric. G is G is just think of the G as dot product.
Okay, so metric is a synonym to dot product.
Yeah.
Okay, thanks.
It's just a The word metric is just, or Riemannian metric to be clear, is just a fancy way of saying, hey, we're redefining the dot product in some way. And we use a little dot when we really meant the original Euclidean metric, and we use G for this new modified metric.
I love it. I'm excited.
It's okay? It's all good? All right. The problem is, even though this all seems good, it's bad. Because you can almost never find this. If you're mapping, for instance, a sphere to a plane, there is no way to find a map that preserves the metric. And that's this classic theorem of Gauss called Gauss's theorem egregium that says there is no way to map a flat space to a curved space without introducing some distortion. And this is why when you try to create a map of the Earth, there's always, distances are always messed up at different points. Or you can look at these weird maps that look like kind of sections of an orange that have been, those are all attempts to minimize the distortion in the map. And years ago, I taught a course on cartography and looked at like the history of all these different maps that map makers have come up with. And they all have different uses because they all have trade-offs involved in where the distortions are. All right, so we've got no hope when we're mapping one space to another, especially if we're doing conformal flattening or flattening. If we're taking a surface, trying to flatten out in the plane to then reverse map a picture onto the surface, we've got no hope of doing this in a way that preserves the metric, okay? It's still important to understand this language because we're going to use it in a minute. So the next best thing is if we can't preserve the distance between points, maybe we can at least preserve the angle between vectors. So now remember, dot product is not the same thing as angle. If you know the dot product and you know the lengths of the vectors, you can reconstruct the angle. But if all you know is the angle between two vectors, even in just traditional vector calculus, if all I know, remember traditional vector calculus, x dot y is magnitude x of magnitude y sine theta sine of the angle between them, right? I can't figure out the dot product if I only know the angle.
I think it's cosine of the angle, right?
Oh, shoot, cosine, thank you. Yeah, sine is cross product, yes, thank you. Matthew's keeping me honest. Whatever, some trig function.
What's the difference of pi over 2 among friends?
Yeah, right, doesn't matter. The point is, the angle is not enough to figure out the dot product. The angle, okay, another way to say that is the angle, knowing the angle does not determine the Riemannian metric. It is a weaker condition. We can hope for maps that preserve the angle, even though we can't hope for maps that preserve the Riemannian metric. So if we're mapping especially a curved space to a flat space, there's no hope of finding a distance preserving map, but we can try to find an angle preserving map. And actually there's an amazing theorem of Riemann, same guy who did the Riemannian metric, called the Riemann Mapping Theorem. And the Riemann Mapping Theorem, it says this is always possible. Given any two spaces, any two surfaces, you can always find a map between them that preserves angles. It's kind of shocking. I mean, to me, this is absolutely shocking. So it is possible to preserve angles, even
They're
though
the same genus, right?
Yeah, sorry, surface is the same genus. Right, I mean, technically the Riemann Mapping Theorem says if you have any kind of disc-like shape, even like say the top half of a sphere, you can always map that to a round disk in the plane. But now you can use that to compose maps. So if I have two surfaces, if I have an angle preserving map to a disk in the plane and an angle preserving map to a disk in the plane, all these maps are invertible. So I can get a map from one to the other so the Riemann Mapping Theorem, technically the statement is any simply connected domain can be mapped to a round disk in the sphere with preserving angles. But a quick corollary of that is you can map any curved domain to any other curved domain by preserving angles. Okay? So an angle preserving map. So Riemann Mapping Theorem says, so Catherine's right, assuming the genus is the same and the number of boundary components is the same and all that, an angle preserving map always exists. So Riemann Mapping Theorem says there always exists an angle preserving Okay, it's assuming the Euler characteristics are the same. All right. An angle preserving map, we now have fancier terminology for that. That's called a conformal map. And I think that's the idea, is we've got no hope of finding distortion-free maps if we measure distortion by how much it alters the metric. But if measured distortion by how much it alters the angle, that's something we could conceivably try to minimize. Find an angle preserving map. And in practice, if you do that and use that for texture mapping, your texture maps look a lot better. I think that's the point here. So that would be the goal, would be an angle preserving map. Now, unfortunately, we are working with meshes. We're working with triangulated surfaces. So if I have a bunch of triangles here, and I want to map that to another bunch of triangles, etc. I'm not drawing this very well. And I'm going to insist that I'm only going to look at angle preserving maps. So that means that this angle is the same as some angle over here, and this angle is the same as this corresponding angle over here, and this angle is the same as the corresponding angle over here. Okay? But now the problem is that's too rigid. That's overkill. Because if all of the angles in a mesh are the same, then it's the same mesh up to just rescaling. All you've done is maybe made your mesh uniformly bigger or uniformly smaller. But you can reconstruct a mesh just by knowing the length of one edge and all the angles. Okay? So it doesn't, if I want to map a sphere to a flat region, I'm not going to be able to do that with meshes if I'm going to insist that all the angles are the same. So the interior angles of all the meshes is not a good discrete approximation of what we mean by conformal. The conformal maps are kind of floppy. You can map any surface to any other surface with a conformal map if there are other characteristics the same. But if we insist that we have meshes and we're going to make sure the angles of those meshes are the same, then we won't be able to do that. Therefore, it's not a discrete version of that theory. Right? We want our discrete theory to somehow mimic the continuous theory, and in the continuous theory, we can map anything to anything. Does that make sense?
Dave, can you describe to me what you mean? Like, let's say that instead of a mesh, we actually had like a thing that we built, and the thing that we built had like rigid angles on it. Yeah. And then in between, the edges were rigid, but they had like a spring on them so that they could stretch and squish some, like a physical object. So the fact that in the continuous setting, we know that there exists a angle preserving map doesn't mean that in the discrete setting, there's a way to flatten out that mesh into another.
Yeah.
Is that the right way of thinking about it? That like
that's right. Yeah.
The discretization like of the little regions actually in some way like you lose a degree of freedom by not having this continuous notion of angle.
How Keenan says it is that we've lost too many degrees of freedom by discretizing it in this way. That's exactly right. Yeah. Yeah. I mean, if we talked about this earlier in the term actually. If I know, let's say I'm starting to build a mesh, and all somebody gives me is the length of one edge and all the interior angles of the triangles. Right? If you just think about it, like that's enough to just totally reconstruct the mesh exactly. Right? I start with that one edge that they know the length of. Now I know this angle of this triangle and this angle of this triangle. Right? I'm assuming I know all the angles. So that nails down the lengths of these two edges. Okay? And then we just keep going. Well, now I build the next triangle. I know this angle and I know this angle. That's going to nail down the lengths of these two edges. Right? So knowing all the angles in one edge length, actually from that, I can compute all the edge lengths. And then now I have an isometry between those. And so now I'm back in the world where I'm only allowing distance preserving maps, which means I just am looking at the same object over again, with another copy of the same object. That's what we call an isometry. We're looking at an isometric object. which is different than a conformally equivalent object. A conformally equivalent object might be the same object flattened out. An isometric object looks just exactly the same. Right? So knowing the angles, all the angles, gives me an isometric object, which is a lot more rigid than a conformally equivalent object. Does that make sense? There's somebody's chatting something.
I was just defining isometric.
Yeah, you were in the word isometric, you hear the word metric, right? And metric means measure. Isometric is same measure. You see all these words, you start hearing them all the time. The word geometry comes from comes from earth. Metry comes from metric. Metric that word goes all the way back to the Greeks, right? So geometry is measuring the earth, and it goes back to the early attempts at cartography, literally constructing maps of the earth. So geometry as a discipline goes back to trying to understand the curvature of the earth. It looks a lot in a lot of cases. It's kind of amazing. Sorry, all a digression because I saw Catherine point that out. Okay, so conformal, so angle preserving maps in the continuous world, that's what we mean by conformal. But if we take that as a literal definition in the discrete world, we don't get a good discrete analog to the conformal geometry in the continuous world. And that's the point. So the game that Keenan likes to talk about is, hey, let's look for mathematically equivalent definitions of conformal and try to discretize those. And then maybe those discrete analogs behave more like conformal surfaces. Okay? So this is where I want to, you pesky, there we go. This is why I want to draw your attention to this reading. So on page 2 of this reading, he goes through a characterization of 7 different mathematically equivalent notions of being conformal. They're all mathematically equivalent, which means you can take this definition of angle preserving, and you can prove that if you have an angle preserving map, then some of these other properties he's talking about are also true, and vice versa. They're equivalent, right? So these other properties that are listed here also imply that you must have an angle preserving map. But the point is, if we keep reformulating this notion of being conformal in these different ways, then maybe we can hope to find a discrete analog of one of these that behaves in the right way. Okay? So the one we're focusing on today is, what do conformal maps mean? What do conformal maps do to the metric? Okay, so I'll talk about this more today. They don't preserve the metric, but they actually do nice things to the metric. They change our notion of distance in nice ways. And then we can take that definition and kind of work it backwards and get a nice discrete analog. Okay? There's some really interesting things here it's worth reading about. There's other ways to think about angles, like it preserves tiny circles. The smaller a circle is, the more that looks like a circle in the target. That's another notion of being a conformal map. There is an analytic definition where you use complex variables to parameterize your surface. And then there's a set of equations called the Cauchy-Riemann equations. And those are just a set of equations using complex variables. And if you satisfy those equations, then you are a conformal map. And we'll talk about those on Tuesday, actually. They're going to come up, the Cauchy-Riemann equations will come up on Tuesday's lecture. Another way that was also going to come up on Tuesday is you can talk about a conformal map as a map that minimizes a certain kind of energy called the Dirichlet energy. And that's closely related to the Laplacian stuff that we just covered. So we'll see the Laplacian rear its ugly head again when we talk about conformal maps on Tuesday. And of course, there's a discrete exterior calculus that's going to come up. The Hodge star is going to be an important operator, mostly as a way to discretize the Cauchy-Riemann equation. So the Cauchy-Riemann equations and the Hodge-Star, we'll see it's just easy to translate between one or the other. And then that's going to lead us to this energy that we're going to minimize to find these conformal maps. Okay, that's all Tuesday. Today we're here. We're going to talk about, so angles up top doesn't work. Okay, that's the first thing to talk about. If you read his notes, it's the first thing he's going to say. In fact, he says that on page 1, that angles are just too much. If you're going to insist that you preserve angles, then you've insisted on too much in the discrete setting. Okay, in the continuous setting, that's the whole ballgame, but in the discrete setting, that's too much. So we have to look at these other definitions, and insisting you preserve angles ain't going to work in the discrete setting. Okay, so let's talk about this number 4 here. Number 4 is looking at what conformal maps do to the metric, and then how do we build discrete analogs of that. And to say that we've gotten a good discrete theory, sorry, I'm trying to move this little slider over. There we go. Just get that out. To say that we've actually come up with a decent discrete theory of conformal geometry, there are 2 characteristics we're going to look for. One is that it's flexible enough to mimic the Riemann mapping theory. Okay, so I should be able to take, in this new theory, I should be able to confine a conformal map from a hemisphere to a flat circle. Okay. Insisting that all the interior angles of the triangles are preserved will not allow me to do that. So it's not a flexible enough theory. Okay. The other quality, though, is the theory should be rigid enough to prove what's called the Uniformization Theorem. Okay, uniformization. I think uniformization was also due to Riemann. Riemann was a big name. Either Riemann or Gauss, like those are the 2 big names in the early days of this history. I think uniformization was probably also Riemann. So let me explain what we mean by uniformization. And hopefully you already understand point 1 here. Uniformization, what we're going to look at is conformal maps between surfaces. And we're going to define the set of all surfaces. We're going to divide the set of all surfaces up into equivalence classes, depending on whether or not there is a conformal map from one to another. Okay, so in other words, you know, maybe I'll have, let's look at tori. It's not true that any torus is conformally equivalent to any other torus. Right? That is not true, that is false. Okay? There are some tori that are conformally equivalent to other tori, but not to other tori. Okay? Not all tori are conformally equivalent. So if I like start drawing every possible torus here, I may have misspoke earlier when I said any 2 maps surfaces with the same Euler characteristic are conformally equivalent. That is not true. It's any, I should have said, be more specific, any 2 simply connected domains like a hemisphere. So that's something that can be flattened out to a disk. Any simply connected domain. So that's simply, the word simply connected just means it's sort of any deformed disk is conformally equivalent to a flat disk. Okay, that's what the Riemann mapping theorem says. It's not true that any 2 tori are conformally equivalent. Okay? In other words, so I'm trying to get to you the notion of conformal equivalence, what that means. So conformal equivalence means I have divided the set of all tori up into equivalence classes. So this is one equivalence class. Maybe here's another equivalence class. Maybe here's another equivalence class. And another equivalence class. And the equivalence relation here is whether or not there exists a conformal map from one to the other. Right? So 2 surfaces are conformally equivalent if there is a conformal map from one to the other. And you can, in the smooth world, you can use any definition of conformal you want, right? So in the smooth world, you could say there's an angle preserving map from one to the other. We can't use that in the discrete world, okay? Is that, you're good? And understand conformal equivalence? Conformal equivalence just means there's a conformal map between the two surfaces. Okay, the uniformization theorem says, uniformization. Says that any surface is conformally equivalent to a surface of constant Gaussian curvature. So you can take any surface, any one of these surfaces here. See, this surface right here, it's kind of floppy. And if you compute the Gaussian curvature at this point, and the Gaussian curvature at this point, and the Gaussian curvature at this point, and the Gaussian curvature at that point, they're all different, okay? But the uniformization theorem says that somewhere in this equivalence class, there is a surface that is conformally equivalent to this guy that has uniform Gaussian curvature everywhere. So it's saying, I can get rid of all the bumps. And if I can find a conformal map where I've gotten rid of all the bumps, I've made this as uniform as possible. Right? So somewhere in this equivalence class, there is a nice kind of round looking torus that's as nice and uniform as possible. Uniform being the Gaussian curvature is the same everywhere. Right?
Is this the generalization of being able to map things onto like a disk or a sphere, like places where the Gaussian curvature would be the same?
Yeah, that's exactly. I think that's, if I understand your question, then I think that's exactly what this means. Yeah, yeah. So one way to say that is, if I take any sphere, no matter how bumpy and messed up it is, I can find a conformal map to a round sphere. A round sphere is the only genus 0 surface with uniform Gaussian curvature. Okay, so no matter how messed up my sphere is, it is conformally equivalent to a round one. So there's a whole continuous family of surfaces that you can slowly modify the metric until always preserving the angles, not always preserving distances, but always preserving angles until it's round. Right? That's what uniformization says. So the interesting thing about these equivalence classes is they're continuous families. You can move between surfaces within each equivalence class through a whole family of surfaces that somehow interpolates from any one to any other. So the uniformization theorem is super powerful. It says that any two-dimensional surface can be continuously deformed through conformally equivalent surfaces until you get to a surface that's as round as possible, where the Gaussian curvature is the same everywhere.
Could you say again why the different like red circles like cannot go to each other?
No. It's just an existence result. Yeah, I mean, you can work out specific examples. There's no reason why I can just tell you right off the bat why you should even believe there are non-conformally equivalent surfaces. Yeah. In fact, there's the space of all conformal structures has a fancy name that's called Teichmuller space. And it's known the dimension of Teichmuller space is 6G minus 6. If G is the genus of the surface, then the dimension of Teichmuller space is 6G minus 6, as long as G is greater than or equal to 2. So if I have a genus 2 surface, there are 6 times 2 minus 6. Teichmuller space is 6 times, so it's 6-dimensional. So there's basically a 6-dimensional family of inequivalent conformal structures for a genus 2 surface. I mean, there's weird theorems like that. I have no idea how to prove that, but you'll hear geometers talk about Teichmuller space a lot, and I've never really understood what they were talking about. But let's not confuse people, though. All right, so that's uniformization. Uniformization says that any surface, okay, so this is the point, is that these two things right here, is we're looking for a discrete theory that does two things. Number one, it should be flexible enough to allow us to flatten out any kind of disk-shaped thing and find conformally equivalent surfaces. But it should be rigid enough that I should always be able to find a conformally equivalent round representative of that conformal equivalence class. Saying a lot of fancy words here. Okay. All right. So I won't say the right way, because but there may be lots of ways to do this. The way that people have found to do this, computer scientists, Keenan and colleagues, I don't know who's responsible if it predates Keenan or if this was one of Keenan's contributions. I actually have no idea. Catherine, maybe you know it. Is the way to do this is with this metric formulation of conformality. So two surfaces are conformally equivalent. The metric won't be the same, but there is an interesting thing that are the same, that this is a different definition of being conformal. This is an alternate definition. If I have a surface here, so I have one surface, I'm going to map that to another surface. Okay. So let's give these things names. I've got, how about my source surface and my target surface? I've already called this map phi. I've got a point here. I've got tangent vectors at that point, x and y. And I've got some Riemannian metric going on here, which allows me to get a number out of x and y. Right? So that's my Riemannian metric over there on my source surface, which is just, again, it's just a generalized dot product. Right? In fact, the dot product in R3 is a perfectly good Riemannian metric. It's called the induced Euclidean metric from R3. Okay, whatever. Then over here on my target surface, I've got the image of P. Okay, and then I've got the image of X under d phi and the image of Y under d phi. Okay. That's what I had before. And over here, I've got G tilde. That's my Riemannian metric over there in my target that allows me to take tangent vectors over there in my target. Okay. Now if I have a conformal map, the metric in the source may be different than the metric in the target. Okay. My dot product, my new revised dot product between those vectors I've drawn x and y in the source, is not going to give me the same number as my new revised thing over there. The angle will be the same. If it's conformal, this angle will be the same as this angle. Okay? But again, we've got to move away from thinking about angles because that's not going to help us in the discrete world. So we're going to think about what this does to the metric and what this does to the metric. So the part of the Riemann Mapping theorem says there exists this function u that will take points in my target space to real numbers such that g of x comma y equals e to the u times g tilde of d phi of x d phi of y. Okay. Don't worry about the e to the u. The only reason I've agonized over this a lot, I think they use e to the u instead of just u there to make sure that this function is always positive. The e to the u is always positive. So don't worry about that too much. The point is there's this predictable function here that tells me how the Riemannian metric changes. And this is an alternate definition of being conformal, is that yes, the Riemannian metric is going to change, but it's going to change in this very predictable way that's governed by this function e to the u, which is always positive. Okay? Now, u may be 0 at some places, in which case e to the u is just 1, so the metrics are the same in those places. Okay? Or u may be 10, in which case the metric's changing by a factor of e to the 10th. but it's changing in a way that's predictable. This function u I can compute beforehand, right? And it's the existence, Kathy, you have your hand up, what's up?
Oh, I was just gonna say, would you visualize the function u as being almost like a scalar field defined everywhere on T, where we're scaling the metric by a certain amount at every point. So we're stretching the metric by a little bit every point, but that point can only be linear. It can't be some other wild function that depends on the location in space.
That's exactly right. Yeah, they're
Okay.
linear. I think that's a nice way to say it, is that at each point, the metric in the source and the metric in the target are linearly related. Yeah, that's right.
So it's like a local squash or stretch on the
Yeah.
input on the pre-image distance,
Yeah.
but it's not anything wilder than a linear, a scalar multiple of that, I guess.
Yep.
Cool. That's so surprising to me.
Yeah. Okay. Oh, I'm already getting short on time. How did that happen? Damn it. Oh, too many windows. All right, I'm just going to jump down. No, stop that. I'm going to jump down to the discrete version just to show you where that is in here. Whoa, I'm way past it. So that's what I told you I want you to read part 3, and that's what part 3 is about. So parts 1 and 2 of these notes are about, I told you at the beginning, there were 7 different ways to characterize conformal geometry. And in part 1 and 2, he goes through the first 6 of those and shows why they don't work. They're either they're not flexible enough, or they're too rigid, or they're not rigid enough to give you uniformization. And finally, in part 3, he says, oh, well, look, if we use the metric scaling, then that gives us this beautiful theory that exactly mimics things, because we get uniformization and we get the Riemann Mapping theory. Okay, so he goes through this, and first of all, we have to understand what's the discrete equivalent of metric, right? Now, metric in the continuous world means we know how long everything is, right? Metric in the discrete world means the same thing. I know how long everything is. And in particular, it means I know how long every edge of my triangulation is. So when they use the word discrete metric, all that means is you know the length of every edge, right? So discrete metric, that's equivalent to saying well-defined edge lengths. I can't write because I'm trying to write quick. I already see I'm tight on time, so I'm writing quickly. So if you know the length between any 2 vertices, then you have a discrete metric. Okay, so let me see if I can make this bigger now. It's really hard to drag this little bar over. There we go. So this is the analog, what he has right here, of the this metric scaling definition of being conformal. It means that at every vertex, you know the value of this function u, and you know that the lengths of the source edges are related to the lengths of the target edges, basically by e to that power. Now, there's a little bit of fuzziness there, right? Because u is only defined on the vertices, but the metric is defined as the lengths of the edges. So that scaling factor is going to be the average of the value of u at one vertex and the value of u at the other vertex. So that's what you're seeing right here. So again, Lij tilde, that's the length in the target surface. What I do is I take Lij and I multiply it by this scaling factor. That scaling factor is e to a number, and that number is the average of the value of u at each vertex. So it's ui plus uj over 2. Okay? That turns out to be exactly the right definition. Whoa, stop that. Exactly the right definition to guarantee that we can uniformize every surface. There's a little bit more to the theory. I'm kind of just trying to give you an overview of this part 3 so that you can go read it yourself and pick up all the details. I got 5 minutes left, so obviously I'm not going to go through all the details of part 3 in these 5 minutes. But there is a second ingredient that I want to get to, which you need to prove uniformization. And once you understand those 2 ingredients, then I think this part 3 will be readable for you, okay? So first, this definition of discrete metric is extremely important. And this is the analog right here. I hope you can see the analogy. This is the analog of this statement right here. So the length in the source, lengths in the source are related to lengths in the target by e to this function, and this function just acts on points. And that's exactly what we have here. Lengths in the target are related to lengths in the source by e to this function, and these are defined on just vertices of the mesh. Make sense? Okay, so I think it's a very reasonable discrete analog. It looks just, in some sense, just like the definition with the Riemannian metric. And these U functions that are defined at every vertex are continuous. So you've got, if this is vertex 1 and vertex 2 and vertex 3, you've got U1 is just the value at vertex 1, U2, U3, these are the values of this function at these individual vertices, right? Now the criteria for being conformally equivalent is, if I look at 2 edges, I'm tight on time, so I'm gonna just cheat and pull out his. There's this notion of the, damn it, don't do that. No. I'm having technical trouble here. Yeah, I've lost my place, I'm sorry, just give me a second. Here we go, metric scaling, there it is. Here it is down here. That's called the cross ratio. So there's a nice theorem that says that if 2 discrete metrics are conformally equivalent, then this ratio of opposite sides of any parallelogram made up of 2 triangles has to be the same. So if you look at what's going on here, we've got L-I-J-I-L. L-I-L is up here at the top. And then we've got L-J-K. L-J-K is at the bottom. That product is equal to the, divided by this product of these 2. That's the cross ratio. So if I have 2 triangles, I put them together, I look at the product of these 2 sides divided by the product of these 2 sides, okay? If I now map that to another surface, and that ratio is the same, all those lengths may have changed, but the ratio is the same, then those 2 surfaces must be conformally equivalent. And that's got to be true for every pair of triangles. So if all the cross ratios are the same for every pair of triangles, then the 2 surfaces are conformally equivalent. Okay? And that notion of conformal equivalence is enough for us to prove, almost enough for us to prove uniformization. It doesn't quite work. As you start to deform all of those values of U, and try to make this more and more, the surface more and more and more and more round, you might get stuck, okay? And that's because as you are changing all of the edge lengths, you're not changing the combinatorics of the mesh. If you had 100 triangles before, you've got 100 triangles after. And if triangle 1 is connected to triangle 5 and 7, it's still connected to 5 and 7. All I'm doing is deforming the edge lengths, but I'm not changing the combinatorics of the mesh. And to achieve uniformization, you might have to remesh that surface. You might have to come up with a new mesh, okay? So there's this one extra ingredient, and to understand this one extra ingredient, I know it's 2:30, it's only gonna take me about 3 minutes to understand this one extra ingredient, which is you have to make sure you're working in a particularly nice triangulation and stay within that family of nice triangulations. And so there's an important word that I know, there's an important word here that people use to describe nice triangulations. They're called Delawny. So a Delawny triangulation has a particular property. And you can really see what's going on if I look at the triangle, these two triangles. So these two triangles, there's something that's not nice about these two triangles. You all know when we did the cotan formula. In fact, let's make this even more extreme. I'm going to look at a really shallow triangle. Okay. When we did the cotan formula, we kept talking about circumcenters. So one of the things we often look at are circumscribed circles. If I look at a circumscribed circle to the big triangle, then it includes the smaller triangle. And for lots of reasons, that's considered bad, okay? It's not a Delawny triangulation if any circumscribed circle contains another triangle. Every circumscribed circle should just contain one triangle. And then it's a Delawny triangulation. Now this is easy to fix. And the way you fix it is you do an edge flip. You take the original pair of triangles. And so I've got these two sides here. That's the left two sides. And the right two sides are here. And I replace this edge. I replace this edge in the middle with this edge here. And now, when I look at the circumscribed circles, I got this one, and I got this one. So there's this nice theorem that says that you can get a Delawny triangulation from any triangulation just by doing a couple of edge flips. You can fix all the places where it's bad. You do a couple of edge flips, and you end up with a unique Delawny triangulation. So that's actually kind of amazing. Usually you get a unique Delawny triangulation unless there's one condition you don't get a unique Delawny triangulation. And this is the key to the conformal geometry stuff, right? In about 2 minutes, I'll stop. There's only one time you don't get a unique Delawny triangulation. Imagine I have a triangle and look at its circumscribed circle. And the other triangle next to it has the same exact circumscribed circle. The circumscribed circle for both those triangles is exactly the same. So now this no longer is a unique Delawny triangulation, because if I do that edge flip, if I replace this edge in the middle with this edge here, that's still a Delawny triangulation. Okay? So the only time you don't have a Delawny triangulation is if neighboring triangles have the same circumscribed circle. Okay, that's it. That's the key now. Okay, so now I'm just going to describe what Keenan says in the notes, and then you can read it a lot slower and fill in the details. So you take a surface, any surface, it's got some awful metric on it, meaning the lengths of all the edges are whatever. Okay, now you've got this function u at all the vertices, and I want to prove uniformization. So I start modifying that u function at all the vertices. That changes the shape of the whole surface, okay? but I'm going to insist that I always have a Delawny triangulation that I'm working with, and I can always get that by edge flips. Okay? The only time I might get stuck trying to change my U functions is if I get to the point where the Delawny triangulation is ambiguous. And then I flip an edge, I still have a Delawny triangulation, and now I can keep going and keep modifying my U surfaces. Then I may get stuck again with my U functions because I have to flip another edge to a different Delawny triangulation, and then keep modifying the U functions, and then flip another edge, and then keep modifying the U functions. Okay, so that's what Keenan says. If I go back over to here, one more thing, this is really the last thing, I promise. That's what Keenan is saying, discrete uniformization. Right here, that's this theorem 1. And the point is, you've got this sequence of triangulations, and he says in this paragraph, this sequence of triangulations is related to each other either by continuously modifying the U functions or by doing an edge flip to get you from one Delawny triangulation to another. Okay? With all of that machinery built up, you can prove uniformization. You can prove, even in the discrete setting, that the discrete Gaussian curvature, now remember the discrete Gaussian curvature, all that is the angle defect at each vertex. So you prove the discrete Gaussian curvature is the same at every vertex. Okay, so you can stay within this world of conformal geometry, modify your U functions, do edge flips, modify your U functions, do edge flip, and in the end you end up with a surface where the angle defect is exactly the same at every vertex on the surface. And that surface is going to be as uniform and as round as possible. If you're working with polyhedral, for example, you're now looking at a regular polyhedron, saying you can take any irregular polyhedron and turn it into a regular polyhedron by doing this. And this was a classic theorem that was an open problem for a really long time. And so there's special cases. There's spherical uniformization. Spherical uniformization is uniformization for tori, and then for higher genus surfaces where you have to work in hyperbolic space. One more very, very quick thing I'll say. This slowly deforming the metrics, always staying in the same conformal equivalence class until you get something with uniform metric. That's all pretty well understood in 2 dimensions. In 3 dimensions, for 3-dimensional manifolds, this was a huge problem. This was one of the $1 million prizes that was won by Grigori Perelman. This whole program set forth by Bill Thurston called the Geometrization Conjecture, and it's got a nice long history. And all this I mentioned is partly because as you read these notes, occasionally he makes references to these things. There's a mathematician in New York named Richard Hamilton, I think he's at NYU, Columbia, who did a lot of early work on this, on the Ricci flow, to deform the metric until you get this nice uniform Gaussian curvature. And that was a big deal back in the, just a few years ago, 10 years ago or so, and answered some questions like the Poincare conjecture that had been open since about 1900. So there's a lot of interesting history here, a lot of stuff to read about. Everything I said was for your own edification. I hope you took something out of it. I hope you do read the notes. The dirty truth is that you won't need any of it. Next week on Tuesday, I'll talk about this entire other approach to conformal geometry called conformal flattening. And that is incredibly useful in computer graphics for texture mapping. And that's the stuff you'll implement when you go to do your written assignment and your coding assignment. Any questions? Are we good? Catherine, you want to add anything?
Nope, I love it.
Everybody good? All right, good luck finishing up your homework for chapter 6, whatever chapter that was.
I'll have office hours. I'm going to take a couple-minute break, but I'll be at the link in Zoom in 5 or 10. Cool.
All right, bye all.
Bye.